Have you ever used a straw to sip juice or seen a tin can collapse after cooling? These aren't just everyday moments, they are brilliant demonstrations of atmospheric pressure in action. Atmospheric pressure is the force exerted by the weight of the air above us. And though it's invisible, it influences many daily actions. What's fascinating is that this pressure acts in all directions, upward, downward, sideways, constantly pressing on everything. And yet, we don't feel it because our bodies are in perfect balance with it. In this session, let's explore some amazing real-life effects caused by this silent yet powerful force. So how does sipping through a straw work? When you suck on a straw, you remove some air from inside, lowering the pressure. Now, the atmospheric pressure on the surface of the liquid is higher than the pressure inside the straw. This difference in pressure pushes the liquid up the straw and into your mouth. It's not suction pulling the drink, it's the atmosphere pushing it. This is a perfect example of pressure difference causing fluid motion, as seen in the diagram where air pressure acts from outside while the pressure inside is reduced. So every time you take a sip, you're putting air pressure to work. Let's now look at syringes and droppers, common tools in medicine and labs. When the piston of a syringe is pulled back, it increases the volume inside, causing the internal air pressure to drop. The atmospheric pressure outside the syringe becomes greater and forces liquid up into the barrel. The same logic applies to ink fillers, eyedroppers, and even fuel injection systems. This is an application of Pascal's law, where pressure is transmitted evenly through fluids in a confined space. As you can see in the diagram, the liquid enters because air outside is working harder than the low-pressure region inside the tube. Ever seen a suction hook stick to a tiled wall? That's physics, not glue. When a rubber sucker is pressed against a smooth surface, air is expelled from underneath. This creates a low-pressure region inside the cup. Now, the atmospheric pressure outside pushes the cup tightly against the surface, holding it in place. Since there's higher pressure outside and lower pressure inside, the cup stays stuck, even holding considerable weight. The diagram here shows air pushing from outside while the pressure beneath the cup remains much lower. Once again, it's pressure difference doing all the work. Here's a dramatic experiment. Atmospheric pressure can actually crush a metal tin. Let's see how. Heat a small amount of water in a tin can until it turns to steam, then quickly seal the can and cool it. As the steam condenses, it leaves behind a vacuum, drastically lowering internal pressure. Now, with much higher atmospheric pressure outside, the can gets crushed inward. The air around us is that strong, over 100,000 pascals at sea level. The diagram shows this clearly. As pressure inside drops, the external pressure wins and collapses the can. It's one of the most powerful classroom demos for air pressure. Let's put numbers to this idea with a solved example. Suppose a flat surface has an area of 0.5 square meters. If atmospheric pressure is 1.013 into 10 to the power 5 pascals, what is the total force acting on that surface? We use the formula force equals pressure multiplied by area. So, F equals 1.013 into 10 to the power 5 multiplied by 0.5. That gives us F equals 5.065 into 10 to the power 4 newtons, or 50,650 newtons. That's the force from just the air on half a square meter. This example shows the sheer magnitude of atmospheric force on everyday objects, even though we don't notice it. The balance of internal and external pressure keeps everything from collapsing. So let's quickly recap what we've learned about the common consequences of atmospheric pressure. Everyday actions like drinking through a straw, using a syringe, or sticking a suction cup all rely on one key idea: a difference in pressure. We also saw how tin cans collapse under pressure differences and how large forces result from even small surface areas exposed to atmospheric pressure. This force is invisible, but its effects are everywhere around us, from our lungs to airplanes, from weather systems to household tools. I hope now you see how atmospheric pressure, though silent, is one of the most active forces in our lives. See you in the next session where we'll explore more fascinating truths of physics that shape our world every day.